Let's talk about circular motion. All right, so what does that really mean? It means things that are going around in corners, like a car going around a corner, or another car going around a corner, and we can have little fishies swimming around and going around in a corner. There's a couple concepts we'll cover here, and this will relate to things we're doing in class and also something you'll see in your book. So let's make the fishy go away for right now. Bye, fishy. We'll make this car go away. Let's just talk about this car right here going around and around in a circle. So you can see turning around like this, turning around like this, turning around like this, right? One thing we know from previous knowledge is about Newton's first law. And Newton's first law says that's the law of inertia, which means that objects like this car, they really want to keep going in a straight line at a constant speed unless they're acted on by some sort of outside force. So if you see something going around in a circle, you know that there's a force acting on it somehow. And there's got to be a net force as well to cause acceleration. It's a different, interesting kind of acceleration because you can actually be going at a constant velocity and still have acceleration. So you can have a constant velocity and a non-zero acceleration, which is strange to think about because actually I should really change this. You can be going at a constant speed and still have acceleration equal to 0. Remember, the difference between speed and velocity is velocity has a direction. So if the direction is changing, then you can still have acceleration. Remember, acceleration is change in velocity over time. So it's really important. If your direction is changing, then you're accelerating. So as you're going around and around in a circle like this, you actually do have an acceleration, right? You are still accelerating. We call that kind of an acceleration a centripetal acceleration. A centripetal acceleration. Centripetal means towards the center. Centripetal means towards the center. So as this car is going around and around in a circle, the direction of the acceleration is actually towards the center of the circle. So it goes this way. The car is actually accelerating in this direction at this point. Now notice when the car moves around and around and around, the direction of the acceleration changes a little bit. So let's take another piece of paper and let's trace the car as it's going around and around in a circle. Good. So there's my car. I'll take up a lot of space in the paper. I'll have it room around a big circle like this, around and around and around and around and around and around, right? So here's the car. And there's the path of the car. So notice that at any one place, the direction the car is going is always going to be tangent to the circle. So that we can represent as the velocity of the car. And the velocity of the car, you can see, is always changing direction. So there's the velocity of the car there, bring me around right here. So there's the velocity of the car right there. You can see that the velocity is constantly changing, right? Now the acceleration of the car is actually in a different direction. So at any particular spot, the acceleration of the car is actually towards the center of the circle. So that's the direction of the acceleration on the car. We can cruise around over here. Wherever you are, the acceleration of the car is actually pointed towards the center of the circle. Anywhere you're rooming along here, pointed towards the center of the circle, just like that. And that's why we call it a centripetal acceleration. Right? Here's the center of the circle right there. What we also know is that if there's an acceleration towards the center of the circle, then there also has to be a force. You remember that force is proportional to acceleration. Really, we write it as F equals ma. So along with a centripetal acceleration, we also have what we call a centripetal force. And the force is in the same direction as the acceleration. Centripetal means towards the center. Okay, so now let's talk about the other word that you sometimes hear, which is this word, centrifugal. You've heard of centrifugal, and sometimes people mix these things up. They say centrifugal or centripetal or something like that. Centrifugal means away from the center. Centrifugal force is a not really a force. Centrifugal force is something that you feel or you sense that you feel as you're going around and around in a circle. So let's say here you are going around in a circle and you're the passenger in the car. So there you are sitting in the passenger seat right there. Imagine what it feels like to be going around this left turn, left turn, left turn, left turn, left turn, left turn, left turn. If you're sitting in the passenger seat, you're actually feeling like a force is pointing on you in this direction. You feel like you're getting flung out towards the door, right? So you've all been in a car before going around a really sharp corner. It feels like you're getting flung towards the outside. So you feel this force going in this way. It's actually not really a force. What you're really feeling is your own inertia that's keeping you going in a straight line. Remember back to Newton's first law, inertia. Things want to keep going in a straight line. So as you come around the corner right here, your own inertia wants you to keep going straight. So the car is actually going to turn away from you, and you're going to feel like you're getting flung out of the car. Once again, here you are. Let's talk about right here. That's your velocity right there. You'd like to keep going in that direction. Well, the car is going to turn out from underneath you, and you're going to want to keep going in this direction. So that's going to feel like a force is pulling you to the outside, when in fact there's no force. It's just inertia. It's only inertia that's keeping you going towards the outside of the circle. There's actually not a force pulling you outside to the outside of the circle. But that's what you feel. Going around and around this circle, you feel the centrifugal force, when in fact what's necessary to make you go around a circle is a centripetal force. So this centripetal force is necessary. You need it to go around a corner. So anytime there's something that's going around in a circle, you know that there's a centripetal force acting on it. If there's no centripetal force acting on it, it's just going to keep going in a straight line, right? And we'll bring this one around instead. Going around and around in a circle, around, 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 around. There's got to be a centripetal force acting on it. If there's no centripetal force, then it just keeps going around in a straight line, right? Let's bring the fishy back, and let's do something else. So I have over here a turntable. I'll bring into the view. There's a turntable. It's just a disc that spins around and around and around. We'll keep going the same direction. We'll keep spinning this way. So you can see that white mark on the disc will show you that it's spinning. So I'll plop the fishy on there. Boink. Hey fishy. And it's a little bit blurry, I guess. The frame rate's not really so good. So there's the fishy going around and around in a circle. What we know is if something's going around in a circle, there must be a centripetal force acting on the fish, just like that. So there's a force that's pushing the fish towards the center of the circle. If there were no force, then the fish would just keep going in a straight line. But we know there's a little bit of friction between the fishy and the surface right here. So it can go around and around and around and around just like that. Now imagine winter comes and this whole surface gets frozen, and we try to put the fish right there on a frictionless surface. If it's frictionless, there won't be any centripetal force available. So as soon as we try to spin this, the fishy is just going to go sliding away in a straight line. So we need that centripetal force towards the center of the circle as the fish goes around and around. Right. Something else to note about circular motion is that as something goes around in a circle, say it's on a turntable like this, the time it takes to go around a circle is going to be the same no matter where you are. So even when the fishy is in the middle right there, it takes the same amount of time to go around the circle as if it's way towards the outside. What we know also is that the outside, this distance right here, this circumference is way bigger on the outside than it is towards the inside right here. So if we're going to talk about the velocity of the fish, it's got a much bigger velocity out here at the outside edge. You can see it's getting way blurrier. And if we move the fishy towards the center, even though it takes the same amount of time to go around, it actually has a smaller speed. That's just something to note about circular motion. Last thing I want to do here is I want to talk about some equations. So let's move this away. Leave the fishy right here. Let's talk about some equations. Physics. Here we go. Bring the cars back. Good. So we have a formula for centripetal acceleration. Centripetal acceleration. And it works like this. V squared divided by r. What are we talking about here? There's our circle, our car is going around again. Whatever the speed of the car is, the tangential speed, that's v, and r is the radius right there. how far away you are. So v squared over r, which means if you're going faster, you have a higher centripetal acceleration. If you're going slower, you have less. Also, as the radius gets smaller, right, you're going to have a bigger centripetal acceleration. It's a little bit confusing because the velocity is actually affected by the radius. That's what I was trying to tell you on the last scene with the turntable. So all things being equal, if you have the same velocity and you're going around a tighter corner, you're going to have a higher centripetal acceleration. If you have the same velocity and you're going around a bigger corner, you're going to have a lower centripetal acceleration. What that means is it's actually harder to make a sharp turn than it is to make a really, really wide turn. We can use Newton's second law, F equals ma, to then write a formula for centripetal force, which is going to be m times that, m times v squared over r. Right? So there's a formula for centripetal force, there's a formula for centripetal acceleration. I think that we should do an example. So let's get another piece of paper going, and we can do an example. Okay, there's our car again. Here we go. And maybe we'll make the fishy go around in a circle. Hi, fishy. So let's say this fishy is going around in a circle like this. There we go. And we'll just make up some numbers here. Let's say the radius is 2 meters and the fishy is swimming at, we'll make the numbers work out easy, 4 meters per second. So let's figure out what is the centripetal acceleration of the fishy. Good, easy to do. Formula just says AC is v squared over r. So that's going to equal 4 meters per second squared divided by 2 meters. I'm going to keep the units going here. So 4 squared is 16 meters squared per second squared divided by 2 meters. So that's going to give me 8. And check out what the units are going to do. Meters squared per second squared divided by meters is going to give me meters per second squared, which is our regular acceleration units. And it's an interesting thing to think about because the speed of the fish, 4 meters per second, is going to be constant. But we still call its acceleration, its change in direction, as meters per second squared. So once again, the speed is the same, 4 meters per second, 4 meters per second, 4 meters per second, the same all the way around. But we still say that it has an acceleration of 8 meters per second squared as it's going around and around in a circle just like that. Now, one other concept we like to talk about, and we'll do this in class as well, is we like to talk about what we call g's. And g's is another way to express an acceleration. So 1g is going to be 9.8 meters per second squared, or about 10 meters per second squared. So instead of saying the fishy has an acceleration of 8 meters per second squared, we can ask, what's the acceleration in g's of the fishy? How do we do that? How many g's? How many g's? Well, that's pretty easy. We just take our 8 meters per second squared, divide it by 1g, which is 10 meters per second squared, and then that'll tell us. Easy math. 10 meters per second squared, which is going to give me 0.8 g's. So we like to express things in terms of g's sometimes. What that tells you is that if you're experiencing 1g of its centripetal acceleration, then it's going to feel like, remember, you're feeling this centrifugal force pulling you to the outside. You feel this fake force pulling you to the outside. And if you're accelerating at 1g, then you're going to feel exactly 1 times your weight pulling you to the outside. Right? If you're accelerating at, say, 5 g's, you're going to experience 5 times your weight. It'll feel like it's pulling you to the outside. Actually, the real centripetal force is towards the center, but because of your inertia, you feel this force flinging you to the outside. So we'll talk about these concepts more in class. This is a nice intro for you, and you can always come back and watch this video again in case you need to do a little bit of review. That's it.